I'm Batman. You've seen me in such fine quality chemistry educational videos as Marvel's got nothing on us. Some chemicals from the Bat Lab. We own the place. Just saying. And what is exactly in the Bat Cave in that chemistry lab?
Today we're going to be talking about buffered solutions. We've talked about pH and pOH and acid dissociation constants and base dissociation constants. If you have no clue what I'm talking about, you need to check the other videos, okay? But there are some in this series here. But what we're going to look at, we're going to be looking at buffered solutions. And I would say a great example of buffered solutions, when aspirin first came out, it was hailed as an incredible drug, and it's still being used today. Aspirin can, give pain relief. One of the things that it does, it thins the blood a little bit, and it makes it a little bit harder for the blood to clot as a result. So if you take an aspirin, you don't want to get a cut because it's going to take longer than usual for the blood to clot. That's the nature of the aspirin. But one of the other things, the main ingredients about aspirin is salicylic acid, which for some people it upsets the stomach a bit. So what do? Well, that's where the makers of Bufferin came up with the idea, hey, if we were to coat the pill with something that would help cancel out some of that acidity brought on by the aspirin, life would be pretty good. And thus was the one idea of how we can use buffer in the real world. But there's also buffer in the blood too, because you don't want your blood's pH to go too high or too low, because that would be bad. Bad for us. We have a very narrow range for that. But I'm here today to talk a little bit about, okay, we've got some solutions here, and so what we're going to do, we're going to calculate the pH of buffered solutions. We're going to do two of them. One of them is we have mixed sodium acetate and, well, this is vinegar or acetic acid. Okay, so we need to find the pH of a solution that is half a molar of acetic acid and half a molar of sodium acetate, and they do give us the equilibrium constant, the dissociation constant of the acid is 1.8 times 10 to the negative fifth. Okay, so what in the world is going on here? Well, there's some things that we need to understand. We need to understand, where does the NaAC come in? What part does this play? Well, we have to look at what are the major species involved here, and we're assuming that the HAC happens to be acetic acid dissolved in water. So what are the players that we're going to have? Well, we're going to have HAC. That's going to be one of our players that we're going to need. We are also going to have the AC minus, okay, because that's going to lose a proton in the process. But we also have a hydrogen plus, which is really what we're interested in finding. And you'd say, well, we also have the sodium plus, also because, hey, that's going to be wandering around in there. And you'd say, but wait a minute, what about the sodium acetate? Wouldn't that be a player? No, not really, because it's going to be broken up very rapidly. Okay, we're not even going to consider it. But it is a key species in here. So how do we go about looking at this? Well, if we look at our basic equation here, we're looking at HAC plus. Oops, I shouldn't say plus, because hey, it is being broken up, right? It's being broken down into, well, H plus and AC minus. And some people are thinking, are we going to do an ice table? Absolutely we are, because that would be kind of a critical thing. So let's take a look here about our ice table. If you don't remember how to do the ice table, you still can get it here, but you can check on other videos talking about equilibrium, and I go through that with you guys. We have our initial, our change, and our equilibrium. Again, you don't have to draw the table the same way that I do it. That's perfectly fine. Now, what did they give us as information? Well, they gave us this and this. Okay. So our original concentration here is going to be 0.5 molar. That's our initial. Well, nothing has happened yet. This is going to be 0 because nothing has been broken up yet. But what about the AC minus? That's where the base comes in, that sodium acetate, because it breaks up and now we have all this acetate floating around. So we can't say that at the beginning there's 0 acetate. That's not true because it's been broken up, okay? It has been dissolved in the water with the vinegar or acetic acid, if you will. So how much is it? Well, we have to look at, again, what's the original amount? And right here it is, 0.50 molar. Okay, so we know this is going to be 0.5 molar. So this is what we have. So in the process, ladies and gentlemen, what's going to happen with us? Well, we know that there's going to be a change because this is going to be breaking down. This is going to gain. And you'd say, okay, but what happens here? It also gains. Because this is being broken apart. Okay? So if this is being torn in two, that means this is going to pick up and this is going to pick up. It only makes sense for that. So now we got our initial, we have our change. Now let's look at our equilibrium. So our equilibrium is 0.5 minus x. Here we have an x. And here we have 0.5 plus x. Okay. So we set up the table like this. We have our initial, our change, and our equilibrium. Now we're shooting for this. This is our target. Now the thing is, it is a strong acid. I mean, no, not a strong acid. It's a weak acid. Okay, weak, remember, it doesn't dissolve a whole lot in water. We go under the assumption of less than 5%, but hey, we can always check that. So, what is that going to look like for us? We're going to assume x is very, very small. So if we remember our equation that Ka is equal to the concentration of our products over the concentration of our reactants. This is an equilibrium constant is muy importante. Absolutely. So let's go ahead and let's plug this in. We're assuming x to be small, so okay, we have 0.5 over, here's the tough one, 0.5. Here it is. So 0.5x divided by 0.5. Say, because this is small, we can discount this. We can discount this, so that means 0.5x and 0.5. So here is our product, so it's 0.5 times x divided by 0.5, which that makes it x. Who would have thought that one? So what does that mean for us? Well, the Ka is equal to x, which is equal to 1.8 times 10 to the minus 5th molar. That's the equilibrium concentration of our hydrogen. Woo, yeah. Can you imagine that? All right. So now, what does that look for us? Well, we got to figure out the pH because that's what they're asking us, right? Well, if you remember, the idea behind the pH is equal to the negative log of our concentration, which in this case is 1.8 times 10 to the minus 5th molar. Now, do you have to write the M in there? No, but I'm just showing you where it's going. And thus, our pH, ladies and gentlemen, our pH is equal to 4.74. And that will take care of the first part of our answer. Okay? You say, wait, there's a second part. Well, we've solved our first question. That first question was, if you go back, calculate the pH of a solution that has a mix of both an acid and a base in it, which we did. But now, to quote some famous TV chef, we're going to kick it up a notch because seldom in life things are that clean. Let's add something. Let's add 0.01 moles of NaOH to our 1 liter solution. Okay, what does that mean? The entire container, beaker, flask, whatever you want to call it, the entire thing of all the liquids, our solutions, is 1 liter. Okay, and that's going to help make some calculations easier. Now we're going to throw in 0.01 moles of NaOH in there. Perfect. Now, here's the thing though. We need to do some stoichiometry. Okay. We need to do stoichiometry, and for some people it's like, chill. This is not the end of the world. Okay? The question comes down to is why? We need to know the number of moles. That's what we need. But wait a minute, isn't molarity the moles? No, it's not, because molarity is a concentration. It's moles over liters. And it doesn't matter how many liters or how many moles. That's the concentration. That's not it. So that means we are very grateful that our 1 liter volume, we're dumping all this stuff in so we can easily figure out the moles. Now, the question comes down to is, what does the NaOH provide? Well, the NaOH is going to dissolve very well. It's a strong base. That means all the OHs are unleashed to create havoc in our solution. Well, what is the OH going to do? It's going after those hydrogens, and it's going to grab it. And when an OH goes and grabs a hydrogen, what do you think is going to happen to the OH? Becomes H2O, water. I still won't drink it though, because solution probably tastes nasty. Okay, so let's take a look on this. So here's some players that we need to look at now. We need to look at our acetic acid. We need to look at our OH minus. The OH minus comes from the NaOH. Remember, it totally dissociates. Okay, and then we have our acetate ion. Those are going to be our key. Those are going to be the key players. So he says we got to figure out what happens. So in this case here, since we are looking at what is our start and what is the end here, this is not quite the same as the ice table. But we do need to know how much damage is the OH going to do to our acetic acid before the rest of it gets there. And that's the key thing. That's the key thing. So at start we have 0.01 moles here of H. We have over here, okay, our 0.5 moles. And then over here, ladies and gentlemen, by virtue, we have 0.5 moles. So this is what we're starting with. Okay, now remember, it is in fact in a 1 liter solution. So that just makes the moles easier. So when they say do the stoichiometry, this is what they're talking about. They're talking about that for the stoichiometry. But here's the thing. This is going to jump on this. The OH is going to jump on the AC because it's going to rip that hydrogen out. You'd say, but wait a minute. What? Yeah, it's going to. This thing is going to dissociate, man, and this is going to take those H's to itself to become water. So that means we're assuming we're losing all of this. This is going to lose this as well. And you'd say, okay, I need to write this, okay, to show the thing. Now, wait a minute. What's happening here, that means it's got to happen over here where we need to add to it. Yeah, we need to add to it. Because remember, you say, well, why do we need to add to it? Well, think about it. If this is taking out already some of this is going to be lonely. And there's going to be more of them as a result of this coming in and interfering with that relationship. Oh, yeah, I know. So let's look at the end of our equation. Let's look at the end of our stoichiometry. So now we have 0.49 moles. We have 0, which is what we expect because all the OHs are just and cancel everything out. All right, and over here we have 0.51 moles. Now we've done the stoichiometry part. This is key because this is canceling out, is doing as much damage as it can to this one. So now let's take a look. Let's see what we've got going for us. Because now we can do our ice table again. Because now we have new concentrations. And the OH doesn't matter at this point because it's gone. But this, it has done its damage here. So let's go ahead. Here is what we got going for us. So this is what we have. We're going to go ahead. We're going to do our ice table again. Okay, I-C-E, ice. So, what is that going to look like for us? Well, hey, now this is 0.49 molar. Remember, those moles are all in 1 liter, and molarity is moles over liter. So 0.49 over 1, bam! Bring on the boom. Now, again, here's our new situation. We don't have any new hydrogens yet. Okay, but we are starting out with a little bit extra AC in there, okay? A little bit of extra AC in there. Now let's take a look at our change. Okay, well, our change, we know this is going to be going out. We're losing stuff here. We're going to gain, and we're going to gain. Okay? So when we look at it, we have 0.49 minus X. Where we have a positive X, and here we have 0.51. This looks more like an S, come on. 0.51 plus X. So that's what we've got, ladies and gentlemen. This is our equilibrium concentrations. Now we've got that. Now again, remember that Ka equals the product over the reactant? We're going to do the same thing again. Okay. So that would mean for us here, we're going to assume X to be really tiny. Kind of like the fiscal responsibility of Congress. Okay? Very little responsibility. So we're going to have 0.51 multiplied by X over 0.49. Yep, that, ladies and gentlemen, is going to equal 1.8 times 10 to the minus 5. That's the Ka that originally they gave to us in the problem. That's the dissociation constant. Remember, we just added a strong base, and that kind of jacked up things. Now, I got to wrap up here. Okay? I am seriously got to wrap up. Okay, so we're going to go 1.04 x equals 1.8 times 10 to the minus 5th. So x is going to equal 1.73 times 10 to the minus 5th. pH is equal to the negative log of 1.73 times 10 to the minus 5th molar. Oops. I gotta hurry. Okay. Our pH is equal to 4.76. Now, our original pH from problem 1 was equal to 4.74. So, our delta pH, or change in pH, is equal to positive 0.02. Ladies and gentlemen, I got to stop here. I hope this helped you out. Take care.